Yo everyone, this is LeetCode 110, balanced binary tree. So we're given a binary tree and we have to determine if it's height balanced. So binary tree is height balanced if the depth of the two subtrees of every node never differs by more than one. Right, so we look at the first example, go to the left, that's a height of 1. Go to the right, the height's going to be 2, depending on whether we go here or here. Doesn't matter. The height's 2 for the right subtree either way, the max height. So 2 minus 1 is 1, so they differ by 1, which is fine, so we return true because it's balanced. It's only not balanced if they differ by more than 1, so if they differ by 1, it's fine. Here, for example, we go 1 for the right subtree, the height's 1, but on the left subtree, the height can be 1, 2, 3, or 1, 2, 3. So 3 minus 1 is 2. The height's going to differ by more than 1 in that case, so we return false. Also worth noting, if you're given an empty tree, it's balanced, so return true. And that can be a case because the number of nodes in the tree can be 0, okay? Just worth noting, it is an edge case that we should handle. So basically for this problem, we want to work our way from bottom up. The reason we want to do that is because we don't want any redundancy because it adds overhead, and as the tree grows larger, the more overhead we have, the redundancy is going to be problematic, right? Like for example, we need to look at the subtrees of every node, right, to determine if it's height balanced. So we look at this subtree starting from this root node, then we look at this subtree. Okay, now let's say we move down and we look at this subtree, and then we look at this subtree. Well, this subtree is the left subtree of 2, but it's also included as the left subtree of the root node, right? So we're looking at it twice. That's not good. So we don't want to be looking at things more than once, right? It is problematic. So we're going to work our way bottom up instead of top down. We're going to basically just use depth first search, right? We're going to go all the way down. And then when we reach a node that has no child nodes, we're just going to return 0 for the left subtree, and the right subtree return 0. Then when we go up, we return 1, right? Or we add 1 to the height, I should say. Then we go here, no child node, so 0. Then we go up, add 1. Okay, the max height of the left and the right subtrees is 1, right? Because they're perfectly balanced. Then we go up, and we add 1 to the height. Then we go to the right here. No child nodes, right? So we just go up and add 1 to the height. Now, at this 2, the right height is 1, the left height is 2. So we take the max of that, which would be 2, and then we add 1 to that. So when we go up, the left subtree at the root node, the left subtree height is 3, okay? Now we go to the right, no child nodes, so we go up and add 1 to the height. Okay, now here, height is 1. On the left subtree, the height is 3. 3 minus 1 is 2. Well, 2 is greater than 1, so the heights differ by more than 1. That's problematic, right? That's not a balanced binary tree, so we return false. Okay? And, yeah. Also, yeah, I don't remember if I said it or not, but, empty tree, we need to take care of that, right? If we're given an empty tree, that can be an edge case that we're given an empty tree as a input. So let's handle an empty tree case first, right? So if root is none, oh my, I don't know if I'm properly indented. There you go. I wasn't getting any color coding, or none of my words were getting color coded, so wasn't sure if it was working right. So if root is none, return true. Okay, because I don't know why, but if the tree doesn't exist, then it's balanced, I guess. I guess I could see the argument for it not being balanced, but for this problem, they decided to say if the tree's empty, it's balanced. Anyways, so let's work our way down. So we're gonna say left is equal to root dff. DFS root.left. We also need to handle going to the right, so we're gonna say this. Now we need to check if it's balanced, right? So we're gonna say the absolute value of left minus right. And again, the left can be less than the right, that's why we have to use the absolute value. And we're gonna say if left is -1 or right is -1 or balanced, greater than 1, return -1. Now the reason we are using this -1 is because let's look at example 2 again. Let's assume this tree keeps going up, right? This isn't the root node. Let's assume the root node's some other node up here. If it keeps going up, again, we already determined that the height differs by more than 1. So at this node. So when we go up, we pass a -1 to the height, right? Because we're not adding to the height anymore. We're just returning -1. So when this node looks at the left subtree, it's going to say, wait, there's a -1 right here. That means the tree is not balanced. So at this particular node, nothing to the right or nothing above it even matters at that point, because we already know the tree isn't balanced. So that's why we're just returning a -1. It basically lets our tree know, right? If we have more to go, it lets our tree know, hey, as we're working our way up, it lets our tree know, okay, hey, this tree is not balanced, right? And think of it kind of like a flag indicator, right? Now, if it is balanced so far, right, we are not returning -1 anywhere. We're just going to return the max of the left and the right subtrees, and we're going to add 1 to it, right? Which would be like adding 1, is what I was showing you down here, right? We're taking, when we look at this subtree and this subtree, we return the max height, which is 2. And when we go up, we do 2 plus 1. So that's when we're up here. That's how we get the max. When we're here at the root node and we're looking to the left, that's how we get the max height we've seen so far. Okay. And then we need to return. This is just so this is our recursive function, and then this return down here is basically calling it for the first time. So we're gonna call it on the root node, and basically if we do not run into a -1, gonna return true. If we run into a -1, we should return false. Okay. Oh, sorry, I forgot to add our base case. That's very important. Root is, if root is none, return 0. Okay. I apologize for that. It's very important to add your base case to recursive calls. Yeah. Right, because if we return -1, right, because we have no imbalanced binary tree, it's going to say, is -1 not equal to -1? Well, no, because -1 is equal to -1, so it would return false in cases where the tree is not balanced. Otherwise, it's going to return true, right? It'd be the opposite case. So yeah, I hope that makes sense. I think I explained it pretty well, but of course, you can ask any questions if you didn't understand something, but I think it makes sense, right? Like, you're just going all the way down, working your way up. If you have a case where the tree's not balanced, you just return -1. So when anything above that looks at that subtree to the left or to the right sees a -1, it basically, you already know the tree is imbalanced. So yeah, I think it's pretty simple. I think I explained it pretty well, but if you have any questions, you can let me know. All right, I'll see you later.